Let's look at the problems from section 2.6 first. There's only one, but the section itself is important. So section 2.6 deals with what we call Koshi sequences. And so Koshi was French, so this is how it's pronounced. The C is like a K, long O, ko, shi, and the accent's on the ko part. He's a very famous French mathematician. And there's only one problem, but this is an important concept, so I'm going to go through it. There's not a lot to do. First, we have to look at the definition. So the definition of a Koshi sequence looks a lot like the definition for a convergent sequence. And we're going to see that that's not a surprise, because a Koshi sequence is a convergent sequence, and a convergent sequence is a Koshi sequence. So that's not a coincidence. Okay? There's a reason why it looks like a convergent sequence. So the definition says, if you give me any epsilon, I can find some natural number n epsilon, so that for any two terms in the sequence past capital N, they're less than epsilon from each other. So let's think about what this means for a second. So this says that once we go past N, any two terms in the sequence, they can be any two terms past N, have to be within epsilon of each other. Have to be within epsilon of each other. In other words, the distance between them has to be less than epsilon, okay? Okay. Now, there are two important facts about Koshi sequences. Just using this one definition, we can show that every convergent sequence is a Koshi sequence. So if it converges, it has to be Koshi. And that's easy to do. This is a good proof to do. It's what we call an epsilon over 2 proof. This is a good proof for you to practice. It's what we sometimes call an epsilon over 2 proof. And the second fact is that Koshi sequences are bounded. That's not too difficult to show. So these are two important facts about Koshi sequences. And the reason why we care about these facts is using these two facts we can prove a very important theorem. And it says that a sequence converges if and only if it's a Koshi sequence. So this means that a Koshi sequence converges, and it means that a sequence that converges has to be Koshi. Koshi and convergent are the same thing. Okay? So this is what if and only if means. You know, if it converges, then it's Koshi, but it works backwards also. If it's Koshi, then it converges. Very important theorem. So we can use this main theorem, just this one fact right here, to show that, to answer all of these, okay? So let's look at the first one. They say, is there such a thing as a Koshi sequence that is not monotone? Well, that's easy to answer, because notice I can replace convergent sequence. Since a Koshi sequence is convergent, this is the same as asking, is there a convergent sequence that's not monotone? And the answer is yes. So the sequence xn, where xn is defined as 1 plus this sequence converges. It converges to 1. Therefore, since it converges, it's Koshi. by our theorem. But it's not monotone. This sequence oscillates around +1, right? Because this sequence, if we look at it, let's just sketch it out really quick here. You know, x1 looks like 0, so the sequence looks like this. Here's 1. This is x1, right? Because it's 1 plus -1 to the first is -1/1. That's 0. x2 is 1.5. Here's x2. Then x3 is on this side because it's 1 minus 1/3 or 2/3. So you can see what happens. The sequence keeps bouncing around 1. Okay? The odd terms are subtracting something from 1. The even terms are adding it. So this is not a monotone sequence. A monotone sequence, all the terms go one way. They're all increasing or they're all decreasing, right? Okay, so notice that the key here is to just substitute convergent. Okay, and I know that there's a convergent sequence that's not monotone. Okay, the second question is a little tricky. You have to read it carefully. A monotone sequence that is not Koshi. Well, let's put convergent in. Can we find a monotone sequence that's not convergent? Because Koshi and convergent are the same thing, right? Okay. Can we find a monotone sequence that's not convergent? Oh yes, of course we can. If we look at the sequence xn, where xn is equal to n, okay, this sequence is obviously monotone, right? So we see that the sequence xn is monotonic increasing. Okay, it's monotonic increasing. But it does not converge. Why? Because it's not bounded. It's not, we usually use BDD for bounded, therefore xn does not converge. We use DNC for does not converge. Okay. And so since this sequence, since convergent sequences are Koshi, this is the same as saying we have a monotone sequence that's not Koshi. Because if the monotone sequence is not convergent, it can't be Koshi, because Koshi and convergent are the same thing. Okay, can we have a Koshi sequence with a divergent subsequence? What this means is a subsequence that does not converge. And the answer is no. So this we cannot have. So the answer here is yes, also. And the answer here is no. And the reason why is if xn is Koshi, then xn converges, and if xn converges, every subsequence has to converge. Every subsequence of xn must converge. And I think that was a theorem that you had earlier. That's an important theorem. Okay, let's look at the last one. Can we find an unbounded sequence containing a subsequence that's Koshi? So again, the smart thing to do is always replace Koshi with convergent. Can we find an unbounded sequence that contains a subsequence that is convergent? Because if we can, since Convergent and Koshi are the same thing, we'll have found an unbounded sequence that contains a subsequence. It's Koshi. And the answer is yes. Okay, and that's easy to do. What I need to do is I need to have one part of the sequence that goes off to infinity and one part that converges. So let's see how to do this. Okay. So let's just define a sequence. I can define a sequence however I want. Okay. So here's my sequence. It's 1 if n is even, and it's n if n is odd. Okay? I mean, I don't have to have a formula. I can define it however I want. This is a perfectly legitimate sequence. Okay? So notice that, So notice that there is a subsequence that's convergent. It's the even terms, right? And since that subsequence is convergent, and convergent sequences are Koshi, this subsequence is Koshi. Very important to understand this. Okay. So this subsequence converges, therefore this subsequence is Koshi because convergent and Koshi mean the same thing. But it's unbounded, right? This is the unbounded part. Right? This part's going off to infinity. Okay. And so that's the answer to that. Okay, these are good problems to think about. These are really good kind of warm-up problems for the exam, I think.